So officially welcome everyone. I am David Porras. I am a 7th grade math teacher outside of Boston, Massachusetts, and the head of content at Mathagon. As you're getting settled in, if you haven't already, please share in the chat where you are in the world and your connection to math education. We're excited to meet you and see who we have with us tonight. The Mathagon team is so excited to kick off our guest speaker series for the 21-22 school year. Mathagon is the mathematical playground with best-in-class virtual manipulatives, engaging and interactive courses, and a wide variety of mathematical activities. Mathagon is free for teachers and students around the world. Please visit mathagon.org to learn more. While you're there, where's my mouse? There's my mouse. While you're there, you could click on Polypad to visit our virtual manipulatives. I'll show you one in our 3D solids. I'll put a dodecahedron on the screen and just move this slider to unfold it to the net and then fold it back up together. I just find great joy doing this over and over and over again. That's Polypad, the virtual manipulatives. You could go to activities. I'm going to leave this to explore a whole host of mathematical activities. There's a timeline of mathematics. There is an almanac of interesting numbers that is wonderful to explore. There are a whole host of problems and puzzles for the last 4 years and more activities that you could explore. And if you click on courses, you could do a deep dive into a mathematical topic of interest to you. Finally, if you're interested on exploring how to use Mathagon as part of your work with students, you can click on 4 teachers at the top, head to events and webinars and see past event and webinars that we've done and sign up for future events. You all signed up for this one, so you maybe signed up for it on the events and webinar page. You could go to tutorials to watch some videos on how to use Mathagon with students. You could click on lesson plans to see over 100 student explorations, lesson plans, puzzles, games, teaching ideas. There's one, in fact, all the way at the bottom because it's in alphabetical order, no slight to our guest speaker, called What Made Me a Mathematician? There it is, by James Tanton. So if you're interested in exploring how James became a mathematician, you can go check out that task. And finally, for some tutorials on how to use Polypad, if you select just tutorials on the left, you can find a number of tasks that will tell you how to use Polypad. That is my quick overview of Mathagon. Welcome again. We are so lucky tonight to spend some time with Dr. James Tanton. I first met James in 2002 or so as I was taking some courses for math teachers in Massachusetts. And it is truly no exaggeration that James has had a profound and deep impact on the middle school math teacher that I am today. A little background on James. Dr. James Tanton earned his PhD in mathematics from Princeton University. He is an author, a consultant, and an ambassador for the Mathematical Association of America in Washington, D.C., and a founder of the Global Math Project, an initiative to transform the entire world's perception of what mathematics can and should be. This program has now reached over 6 million students and teachers across the planet. In fact, I'm going to deviate from the script here and tell you that Global Math Week 2021 is coming October 10th through October 17th. So you can head to globalmathproject.org/GMW. Maybe James can drop that into the chat, and you can see the whole host of events that are happening during Global Math Week 2021. So I encourage you to head to that link and sign up for all sorts of amazing mathematical journeys of joy that will be taking place that week. James has taught mathematics both at university and high school institutions. He advises on curriculum, consults with teachers, and gives demonstration classes, lectures, and professional development sessions across the globe. James is also a recipient of a Joint Policy Board for Mathematics Communication Award for 2020. You can follow James on Twitter at James Tanton. Thank you for indulging with me for a few minutes. It is my great honor to turn it over to Dr. James Tanton.
Well, goodness, thank you so much. Oh my goodness, what a joy and an honor to be here. David, I think, is a tremendous fellow, and the work he's doing with Mathagon, which is a tremendous program, is just tremendous beyond belief. Talk about a huge gift to the world. What Mathagon's provided for the world is just beautiful beyond belief. Do check it out. And thank you so much for coming here. I see many familiar faces, so thank you. You know everything I say, those that are already here that know me. But thank you for coming along nonetheless. And thanks for a fine showing from the antipodal regions, from New Zealand and Australia. I'm so impressed. I know it's midday for you guys down there in Australia right now, so it's not too bad. But I see some folks from other part of the world. I'm sure it's the middle of the night right now, so I'm honored. Okay, but those who do know me know I have a very important question that I have to ask first before we do anything. That's the only thing I actually care about for tonight's presentation. Does everyone on this call right now, is everyone here aware that there is an international salute to mathematics? Do you know there's an international math salute? Some thumbs up and some people doing this. So I've got some faces on the screen. Yes, yes, okay, and yes. Okay, some very vehement yeses. All right, not everyone said yes right away. So we shall start this evening, this afternoon, this morning, which is part of the world you're in, with the international salute to mathematics. And I'm not making this up. If you Google international math salute, you will find this. It begins as follows. So you need your arms completely free. So you put down your coffee cups or your drinking glasses or whatever snack you got in your hands. Everything's hands-free, and start out as follows. Put your arms out front. You make your hands look big on the screen. Ooh, big hands. Then you go right hand over left hand. That's the hard part, right over left. All right, everyone's good, everyone's doing it. Fabulous, right over left. Then you go palm to palm. And then the salute gets weird. You wiggle your little fingers. Then you wiggle your thumbs. Then you wiggle your little fingers again. And then when you're ready, just come on back. Whoa. Some people did it, but some people looking a little bit bemused. Rosin, well done. Yes, well done. Nick and family, well done. Okay, but for others, should I do it again? Would it be helpful if I did it again? Feel free to type in the chat or just unmute yourselves. We're all friends. We're just an intimate small group. Feel free to say, yes, do it again, James. Must do it again. Any nods for doing it again? Yeah, a couple of nods.
Do it again. I want you to do it again.
Okay, all right. So I'm going to do it sideways, a different angle. Arms out front. I think you can see me wrong. I've got a white wall. That's good. That's very handy. Right hand over left hand. So you can see it really is my right hand on my left hand. No cheating there. All right. Then it goes palm to palm and clasp those fingers. Wiggle the middle fingers. Woo! Wiggle the thumbs. Woo! Wiggle the middle fingers again. Woo! I don't know why I'm making silly noises. Forgive me. And then when you're ready, just come on back. Oh, Elizabeth's got it. Other people have got it, but Bannon hasn't got it. She's looking very stuck. And Jay Palmer, looks like you're stuck as well. Would you like some help? Shall I help out a little bit? Very handy. Yes, it is very handy. I'll help out a bit. I'll give half a hint. I'll give some half help because actually there's a really good maths lesson in the salute. I've given you a problem. You've got a problem right now. How do I do the salute? In fact, you even know what the final answer is meant to be. You know the final answer is meant to be untangled hands like that. So what's a very good strategy if you've got a problem in maths or life, you know what the answer should be? Any thoughts on what's a good strategy? You've got a problem and you know what the answer should be, or at least have a good thought what the answer should be. What could you do? What's a good strategy? Work backwards. Yes, it's a very simple idea, but it's a very powerful one, and people often forget about it because it's so powerful and it seems so simple, but it's really good. Mathematicians do all the time. So I will half help us out. Let's start with the answer and work backwards. You have to say to yourself, okay, I want to reverse engineer this. Where did it come from? Well, it must have come from my hands being turned over. Okay. And then you ask, well, where did that come from? Well, it must have come from my fingers being unclasped. Okay, so I've halfway helped. We start at the end and we got to this funny feeling middle position. I bet that feels very different to you. So your job now is to now start at the beginning. Can you get to that same funny feeling middle position somehow? Because if you can, then you're all set to come on back. So that was half my help. I got us halfway backwards. Your job is now to go halfway forwards and meet in the middle. All right, so here's the deal. While I'm being particularly boring for the next 48 minutes, you can secretly turn your camera off and practice this behind the scenes, just to amuse yourself until we're done, and then turn the camera back on and say, yay, yay, great talk, even though you're doing this all the time. But if you want me to give away the answer, I will. I promise to give you the answer if you ask me to. All right, so what you came here for tonight, this morning, this afternoon, is a dozen proofs that 1 equals 2. I am going to prove that 1 equals 2 a dozen times over. If you don't like one of my proofs, it doesn't matter, because there'll be 11 others that will convince you. I bet by the end of tonight, you'll be convinced that 1 really does equal 2. And to get going with this game, I have to start by sharing my screen. So forgive me while I fumble. Everyone fumbles on Zoom where they try to share their screens, all that sort of stuff. But here I am, sharing my screen, except I can't see my own screen. Now I can see my own screen. All right. Are you seeing a title to a talk? A dozen proofs that 1 equals 2. And can you see my hands on it, looking all, I don't know what color they look in this camera. All right, here goes. I'm going to give a dozen proofs that 1 equals 2. Here comes proof number 1. In fact, I'll start with a famous piece of history. This is a historical proof. It goes back about 500, 600 years to Guidobaldo del Monte, who was a friend, my camera needs to focus, a friend and a patron of Galileo. So he was a big dude back in the 1500s. And he did something astounding. He claimed he could create something out of nothing. And he went even extra bold and said that meant God exists. He thought he proved that God exists by creating something out of nothing. So that's pretty bold. But let me show you what he did. Here's how he thought he created something out of nothing. He started with the number 0. He said, okay, there's nothing. Well, 0 equals 0 plus 0. Okay, that's fine. This also equals 0 plus 0 plus 0. In fact, you can add as many zeros as you like. It will still be 0. Just keep going, keep adding zeros. It'll still be 0. And then he said to himself, well, okay, what if I write 0 in a funny way, like 1 take away 1, plus 1 take away 1, plus 1 take away 1, plus 1 take away 1, and just did that. And that's still just 0 plus 0 plus 0 plus 0. Nothing funny there. He said, well, hang on. But what is 1 take away 1? It's really 1 plus negative 1, plus another 1 plus another negative 1, plus another 1 plus another negative 1, plus another 1 plus another negative 1, and so on and so on and so on. He said, okay, well, that's still correct. There's nothing wrong with that. He said, well, hang on. What if I put my parentheses like this instead now? Oh, there's a 1 there, and so on. So we do that. Now I see a 1 plus negative 1 plus 1. That's 0. Plus, a negative 1 plus 1. That's 0. Plus, a negative 1 plus 1. That's 0. And so on forever. And of course, 1 plus nothing plus nothing plus nothing is 1. He created something out of nothing. Now, what I'm going to do is add 1 to both sides. 1 plus 0 is 1 equals 1 plus 1 is 2. So I conclude from Guidobaldo del Monte's proof that 1 equals 2. Done. I'm finished for tonight. That's it. Thanks for coming. Lovely to see you. Do you have a problem with this proof? Do you have any issues with this proof? Does something worry you about this proof? I'm wondering what you think. Feel free to type in the chat or just maybe unmute yourself. There's only 70 people with us today, so surely we'll be a good intimate crowd. Any thoughts?
I see a hand raised from someone, Zita Zara. Feel free to unmute and just chime in.
Okay, thank you so much, sir. So basically, I know you group stuff together, but like it's not pure factorization. You just grouped it, and I don't know if you're just allowed to group like that with brackets. I don't know. I'm in grade 10, so I don't know anything. I'm not suggesting I'm right, but like
I love how you're thinking, because
I don't like the way you factorize, because if you're factorizing, you have to look at common factors or a pattern. So you assuming that your pattern starts towards the right, sir. So for me, I don't like the way you group, because I don't know if I'm correct, but the way you're grouping, I don't know if that's based on like a sound mathematical principle. I don't know if I'm right.
Okay, but I love your brain. Your brain is beautiful, because the other people agreeing with you in the chat. There really is problems here with the grouping. It is true that if I did like a finite little sum, like 2 plus 3 plus 4, suddenly equals 2 plus 3 plus 4. If I want to group the first 2 and then add 4, that's fine. Or if I want to group the last 2 and go 2 plus 7, that's fine. Certainly, in a finite sum, it's okay to group things with these brackets or these parentheses in different ways. But the issue is, this is infinite. I'm doing infinite work here. And this started worrying people in the 1500s. They had exactly the same question you had. They said, hang on, we can regroup things any way we like for finite sums, but maybe infinite is different, because if we start doing the same thing with infinity, it gets weird. Things get weird and worrisome. We don't know if the rules of algebra still apply for infinite sums, and people started getting nervous and thinking maybe the standard rules of algebra don't necessarily apply for infinite sums. So people got very nervous playing this sort of game and said, this can't be right. Something is philosophically wrong with Guidobaldo's proof here. Maybe the ordinary rules of algebra no longer apply. So your brain, Zeta Zara, is actually right on mark. This got people worried. Okay, all right, so that proof. Okay, maybe that one's too worrisome. So let me do another one. Now, I'd be very remiss if I didn't do this proof. I'm sure everyone has seen this proof. It's a classic proof by algebra. And this proof is very standard, but I have to do it tonight just to be complete. Let x be the value 1. So let x equal the value 1. Okay, I declare x to be the value 1. Done. Well, if that's true, then x squared take away x must equal x squared take away 1, because I just said x and 1 are the same thing. All right, okay, so that must be true, no worries there. And then I say, okay, but this looks like I'm in an algebra class, because I could be in a 10th grade algebra class. There's a common factor of x on the left. X times x minus 1 is what the left-hand side is. Oh, and the right-hand side is what people call a difference of two squares. It's really x squared take away 1 squared. So it factorizes, it also factors like this. People say factorize in the UK and Australia. People say factor in America. So I'll try to use both words as much as I can. All right, so x times x minus 1 equals x plus 1 times x minus 1. Oh, a common factor of x minus 1 is to divide both sides by x minus 1. That leaves me with x on the left equaling x plus 1 on the right. But let me remind myself, x is the number 1. Oh, good. So 1 is equal to 1 plus 1. 1 equals 2. Aha! Happy fellow I am. We did it. Now we proved 1 equals 2 without getting into weird issues of infinity. What do you think? Oh, people are saying I'm doing a naughty thing by dividing by 0. You know, this is the classic proof. You often see this on Twitter and Facebook and stuff. This proof makes its rounds every 15 years or so. You're right. We said x equals 1, and it's true that 1 squared take away 1 equals 1 squared take away 1. There's nothing wrong with that line. And this line is actually correct as well, because it's saying right now that 1 times 1 take away 1, 1 times 0, equals 1 plus 1, 2 times 1 take away 1, 0. That's actually correct. 1 times 0 does equal 2 times 0. But look what I did. I divided both sides by x minus 1. I divided by 0. And that got me into trouble, because that line is now saying 1 equals 2, because I can't divide by 0. Not allowed. Naughty, naughty James. You cannot do that. You caught me dividing by 0. If you divide by 0, all sorts of illegal things can happen. That means this proof is broken down. All right. Okay. Don't worry. We've got 10 more proofs. In fact, we've got 11 more proofs. I've got a bonus proof by algebra. Here's another proof by algebra. Since that algebra argument was shot down, here's another algebra argument. Let's try this one. This one's a bit weird, but just bear with me. All right, I'm going to ask us to solve the equation x squared plus x plus 1 equals 0. So we're like some pretty high school maths, sophisticated maths right now. Don't worry, we'll go back to kindergarten, all sorts of things later on, but we'll do all sorts of maths. By the way, x is definitely not 0. X is definitely not 0, because 0 squared plus 0 plus 1 is not 0. So 0 is not a solution. So I know x cannot be 0. So let's divide everything through by x. I know I'm not going to divide by 0 this time. And that gives me the equation x plus 1 over x, x plus 1 plus 1 over x equals 0. So x can't be 0, therefore I'm allowed to divide by 0, and I've got that equation. So that tells me x equals negative 1 take away 1 over x. Let's get x all by itself. Now let me do something weird. I've now got a formula for x. Let me take that formula and substitute it back into the equation. So that's now telling me x squared plus negative 1 take away 1 over x plus 1 is meant to be 0. That's the equation I'm meant to play with. All right. The nice thing about that is that negative 1 and positive 1 cancel out. So this is really the equation I'm playing with. X squared minus 1 over x equals 0. Let me multiply. Let me bring that on the other side. X squared equals 1 over x is what the equation I'm really playing with. Let me multiply both sides by x. So that gives me x cubed equals 1. That's the equation I'm really playing with. Oh, I know the answer to that. 1 cubed equals 1. X must be 1. Great. So 1 is a solution to our original equation. 1 is a solution to our original equation. So that tells me, oh, brilliant, James. Then 1 squared, which is 1, plus 1 plus 1 equals 0. I've just learned that 3 equals 0. Let me subtract, let me divide by 3. 1 equals 0. Let me add 1, 2 equals 1. Beautiful. Yes, yes, yes. Whoa, whoa. What do you think of that one? This one's for the sophisticated mathematicians. I've gone way high up in mathematical sophistication. Any thoughts on, you didn't substitute x in both spots? No, it's true. I just chose to substitute x in one spot. Is that bad?
We have a hand raised from our 10th grader again, Zita.
Oh,
if you want to try.
Okay, Zeta, you've got the brain. What are you thinking now?
I don't know, like, I don't like the way, you know, when you moved everything to the right-hand side and you said you like assumed you divided by x. I mean, you divided everything by x, right? And now you're taking to the other side. But when you're going to do like solve equations, you've got to get rid of like when I say the denominator, you can't just like assume and like solve and say x cubed equals to 1. I think that's the first problem. I don't know if I'm correct. Like,
We've got a first thing problem.
I don't know. Okay. I would have used the quadratic formula because I know that this equation doesn't have real roots. You can't.
Okay. All right. Okay. Say that you're onto it here. All right. So here's the issue. Actually, everything I did is valid. If x is a solution here, then x must be a solution to that, and 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 that, and that. Any solution to this must be a solution to that. But I didn't claim it works backwards, that every solution here is a solution back in the original one. I happen to just choose one particular solution there. Turns out this has three solutions. And as you said, turns out 2 of the solutions aren't real. They're imaginary solutions. And if you did the quadratic formula on that, you'll get 2 imaginary solutions. Turns out I happened to pick the wrong solution in the final equation. I kept doing lots of weird algebra. It's true, anything that works here must work there as well, but I never claimed that everything that works here must work back in the original. I didn't claim I could go backwards in this case. So I happened to choose the wrong solution of the 3. Turns out the other 2 solutions to this really do work. So I was being naughty and just happened to choose the real solution, but you pointed out this doesn't have real solutions. I was naughty and chose the wrong of the 3 solutions. I should have chosen the 2 not real solutions. And actually, then it turns out to be okay. All right, my brain's hurting. That was too hard. Let me go back to grade school. Let me go back to primary school. Here's a proof that 1 equals 2 by fractions. So here's the amazing thing. Not many people realize this about fractions. For example, look at the very first fraction I've got. That's 26/65. By the way, 26 is 2 times 13, and 65 is actually 5 times 13. So I've cancelled out a common factor of 13, and this is really 2/5, which means actually I could have just crossed out those 6's to begin with and get 2/5. That's correct. People don't realize that in base 10, it's actually okay to cross out 6's, 3's, and 9's, those multiples of 3's. For example, 16/64. Well, if I cross out the 6's, I get 1/4, 1/4. That's correct. 16/64 is 1/4. 49/98, it's okay to cross out 9's. That would leave 4/8. And guess what? 49/98 is a half. 4/8 is a half. That's correct. Here's a weird one. 163/126. Let me turn my calculator on. Let's do half my brain. 163 divided by 326 equals a half. Cross out the 6's, cross out the 3's, and what are you left with? Indeed, a half. Whoa, if you start repeating numbers like, so I did something crazy, let's clear. 26666, oops, 46, yep, divided by 4 6's, 1, 2, 3, 4, 5. Cross out the 6's, I claim it's 2/5. It should be 0.4. It is! People don't realize that you can, in base 10, you can just cross out 3s, 6s, and 9s, and all is okay. So let me have fun with that. In that rule then, let's say 13 32ths would have to equal, cross out the 3s, 1/2. All right, so let me multiply both sides by 2. So 26 32ths equals 1. Let me multiply both sides by 32. So 26 equals 32. Let's subtract 26. So 0 equals 6. Let's divide by 6. 0 equals 1. Let's add 1 to both sides. 1 equals 2. There, I got it. 1 equals 2. I love it. So there's my proof that 1 equals 2 by fractions. What do you think of that one? Someone says 13 32ths isn't a half. What?
I think you handpicked your fractions.
Handpicked my fractions. Do you know what? I chose 5 fractions that by pure coincidence happened to work this way. What I said that you can cross out 3s, 6s, and 9s is not true. I actually just chose 5 that by pure coincidence happened to work. Because yes, you're right, 13 32ths doesn't equal a half. This is just nonsense. Oh, okay, you caught me. I was actually trying to pull the wool over your eyes. But actually, it's really fun to try to come up with more examples. When I, actually back in my Boston days when I was teaching in school, I gave this to my high school students. And one student was so smitten that she shared this with her father, who became so smitten. And her father sent me a note with this example: 1, 2, 3, 4, 5, 6, 7, 9. So you missed the number 8. Over 9, 8, 7, 6, 5, 4, 3, 2, and you missed the number 1. So take that crazy fraction, cross out the common numbers. So there's a common 9, there's a common 7, there's a common 6, there's a common 5, common 4, there's a 3 and a 2. And you're left with 1 on the top and 8 on the bottom. And guess what? That turns out to be true. He found that crazy example. So if you want to have fun, it's actually good to have fun to try to find fractions that by luck, this is just luck, no deep mathematics here, just pure luck that this happened to work. All right, you've got me on that one. So we've got 3 proofs down, but don't worry, I've got more proofs. Proof number 4. This is mighty fine. I'll get it yet. We'll prove that 1 equals 2. I know I will. All right, here's proof by complex numbers. So these have been mentioned today already. The number I is this weird number, the property that I squared equals -1. So I'm going to do a one-line proof. One-line proof. Here's the number 1. I claim it equals I squared plus 3 divided by 2. I think I'm right, because that's -1. -1 plus 3 is 2 on the top, 2 on the bottom. Yep, that's 1. So let me just tease this apart. I squared is I times I plus 3 all over 2. That's fine. That's all good so far. But what is I? Well, I is the number to the square root of -1. So it's the square root of -1 times the square root of -1. Whoops, -1 plus 3 all over 2. All right. If I can write neatly, that would be helpful. All right. So square root times the square root. That's the square root of -1 times -1 plus 3 all over 2. -1 times -1. Oh, that's one of those annoying things. It equals +1. So this is actually the square root of 1 plus 3 all over 2. What's the square root of 1? It's 1. So that's 1 plus 3 all over 2. That's 4 over 2. That's 2. 1 equals 2 in one line of math. Whoa! That's a good one. That's a good one. That's got to be true. There it is. Yes, there it is. So people are already writing things in the chat. There's something mysterious about this one. The square root laws. You know, this is the thing. This is the thing. This is the correct way to define I. But the trouble is, this symbol is a symbol from geometry. When everything is all about, you know, positive areas, positive side lengths, all the rest. It makes sense in geometry. If you start going to negative numbers, things get out of whack. Technically, this is saying, well, I squared is 1, that actually there are 2 square roots of -1. Square root of -1 is either I or the negative version, plus or minus I. Every square root has a plus or minus version. So my trouble is, right here, when I define I to be the square root of -1, I don't know what you mean. Which one do you mean? So technically we're a little bit off by there. It could be a plus or minus 1 there. which is fine, that's still plus or minus. And then actually there are two square roots of positive 1, either +1 or -1. So this is actually either plus or minus 1 again. And all we've actually proven is 1 equals 3 either +1/2 or 3 -1/2. And yes, that's correct. It is one of those. But I don't know which one it is. And I have to choose again the wrong one. This is dangerous. When people say I is the square root of -1, we're in trouble. We can actually be off by a sign if you're not very, very, very careful how you play with square roots, especially when you start multiplying square roots that people are saying in the chat. This is very dangerous. All right, okay, my brain is hurting too much. We've got to go back, way back to kindergarten. Now let's go to preschool. Preschool. Here's a proof that 1 equals 2 just by coloring. We're going to just color things in. So let me get a nice color. I'll choose the orange. Orange is good. Here's a square. Here's another square. I'm going to color this side of the square. Ooh, that used some ink. I used some ink to do that. Great. Over here, I'm actually going to color in the whole square. I'll do the bottom and everything inside, all the sides, and I'm going to color the whole thing. Whoa. That definitely uses more ink. There's no doubt about it. There's common sense. Some ink, definitely more ink. Right, now let me tell you about the size of the square. It's actually a 1/2 meter by 1/2 meter square. So 0.5 a meter, 0.5 a meter. That's the dimensions of the square. So let's ask, how much ink did I actually use? Well, here I just did one length of the ink here. I did 0.5 units of ink from that side. Here I did the whole area, which is 0.5 times 0.5. 0.5 times 0.5 is 0.25 units of ink. Okay. Oh, this was some ink, and that's more ink. Okay, that must mean this amount is actually less than that amount. 0.5 is less than 0.25. Let me multiply everything by 4. 2 is less than 1. And everyone knows that 1 is less than 2. That's just common sense. 1 is less than 2. So I guess the only way out of that predicament is that, oh, they must be the same number. 1 must equal 2. There's my proof that 1 equals 2 just by coloring. Pure coloring in. Now I feel satisfied. Now I think we've got it. Proof number 5 has done it. What do you think? What do you think of that one? Someone agrees with me. Fabulous. Yet other people don't. I know, I was being sneaky. I use the word units. I'm being very bad. I actually use a unit of length there. That I guess should be meters. This is actually a unit of area of meters squared. I can't actually compare different things. 0.5 meters compared to 0.25 meters squared. Nah, silly James. Silly, naughty James. I was pulling the wool over your eyes again. All right, that proof is out the window. Oh, okay. All right, but don't worry. I'll do more geometry. Proof by geometry, here it comes, even more. This time I'll go back to, whoops, let's get there it is. Here's a 1 by 1 square, and I'm going to try to work out the length of the diagonal. All right, so this is like a basic school geometry now. I guess Pythagorean theorem helps me, because I can say that d squared must be 1 squared plus 1 squared. Yep, a squared plus b squared equals c squared, as everyone seems to say. D squared must be 2, so d must be the square root of 2, which is about 1.414, if I remember correctly. All right, so the length of that diagonal is about 1.414 units, the square root of 2 units as a length. But let me come to that length in a different way. Here's my second way. I'm going to actually approximate that diagonal by doing, I don't know what this is going to show up. Maybe this doesn't show up, we'll see, as staircases. For example, here's a very crude approximate of the diagonal. I've got red steps and I've got blue steps. And you can see as I make this little staircase, that's kind of like the diagonal. But here's the question. How long is that path? And I can see that path is, all the red stuff is the same as the bottom side length, and all the blue stuff is the same as the side length. So I guess that red stuff adds up to 1, that blue stuff adds up to 1. So the length there is 2 units. That staircase is 2 units long. But if I make a better staircase, it closer approximates the diagonal. So here's all the red stuff, which I can see again actually matches the bottom length. And here's all the blue stuff, which matches the side length. I can see the length of that staircase is also 1 plus 1 is 2. In fact, I did an even finer staircase. That little wiggly line has 2 units of length. I did a finer one and a finer one. I keep going finer and finer ones. well, I must be getting close and close to the true diagonal. This length has 2, this length has 2, this length has 2. Every approximation has length 2. I can only conclude that the length D must be 2. It's 2 in every possible approximation I do. All my approximations are getting better and better. That length must be 2. So my previous answer, square root of 2, is the same as that answer, 2. Therefore, I deduce that square root of 2 is the same as 2. Let me square both sides. 2 is the same as 4. Divide both sides by 2. 1 equals 2, and I've got it. Woo! Proof number 6 did it. Halfway there, and we finally got there. This proof is completely wrong. Oh my gosh, that's bold. Okay, why is it completely wrong? Approximations don't keep getting better. Well, here's the thing. This was a big crisis in the 1800s as people were really trying to think about, well, what does it mean to approximate things? What does it mean to get better and better approximations? It is true in some sense that these staircases are actually becoming better and better approximations of that diagonal. Every point on the staircase is actually moving closer to the diagonal. So point-wise, everything's becoming more and more like the diagonal. These staircases do converge to the diagonal point-wise, but only in that sense. They don't converge in terms of length. They don't converge arc length-wise. We have point-wise convergence, but we don't have length convergence, which is very confusing. This drove people insane during the 1800s trying to understand limits. And they realized there's lots of different types of limits you can think about. Do you want to see just where the points are moving to, in which case that's fine, but that tells you nothing about lengths. Or do you want to say what the lengths are moving to, which is fine, but it's not telling you about limit lengths anymore, things go out of whack. So that was actually a very important example in the history of mathematics. As people were trying to make sense of calculus in the 1800s, they're trying to make sense. What does it mean for things to get better and better approximations? How do we know things really converge? What does converge mean?
We have another hand raised from Zeta Zara, James, if you're interested.
Okay, go for it.
Like the thing is, like if you look at the Taylor-Maclaurin series, I don't know if I'm saying that correctly. Like I was trying to teach myself limits and series. It's like point of convergence, because you're not going to get the exact thing is converging at like a middle, like with squeeze theorem or something. So you can't say it's going to converge at that point. That's what I think. I'm not sure if it's correct. So that's why it would be false, because you can't keep adding, because your different edges of infinity are not the same. I don't know if I'm saying it the right way.
Okay, but that's it. But you're right. There's lots of subtle issues that are very hard to think through. It took mathematicians decades, if not a full century or more, to figure this out. And what makes me sad, actually, is then we have students who learn calculus say, well, just do this because it's obvious. It's not obvious. Mathematicians were really stuck by this stuff for centuries. There's a lot of subtle things. In fact, let's talk about the infinite some more. Here's a proof by rearranging. Let's do this comes from a Taylor-Maclaurin series of a famous series function. I will work on one specific value. This infinite sum, 1 take away a half, plus a third take away 4, plus a fifth take away 6, plus a seventh take away 8, and so on. There's definitely a pattern there. Now, you will learn in calculus, this does actually have a finite value. The more and more terms you do, it gets closer and closer to being at 0.69, the log of 2. So this actually has a finite value. X really is an actual number. But even then, even if you can prove its convergence, things get strange. Because look at this. Let me double X. Let me do 2 X's. That means I have to literally double everything I see. 2 times 1 minus 2 times a half plus 2 times a third minus 2 times a quarter plus 2 times a fifth minus 2 times a sixth plus 2 times a seventh minus 2 times an eighth plus 2 times a ninth, and so on and so on. I think I did that correctly. Can you just double check me? Did I do all those doubles correctly? So someone says in the chat, yes, James, you're fabulous and you did it correctly, because I really can't do arithmetic. I'll agree. Okay, I made a mistake. Oh, yes. Okay, someone said yes. All right. Okay. Now look at what we've got. I've got 2 take away 1. That's just 1. I've got a minus a half. There's a minus a half. I've got a 2/3 take away a 1/3. That's plus a third. I've got a minus a quarter. Minus a quarter. I've got a 2/5 take away a fifth. Will I have a take away a fifth somewhere? I will. So I went down further. There would have been minus 10th somewhere, which would have got doubled. I would have a minus fifth down here. I would have a plus 1/5. Do I have a minus 1/6 anywhere? I will, oh, sorry, I made a plus there, but if I do it, when I go to the minus 1/12, I double it, I have a minus 1/6, and so on. So actually, you get back to the same sum. This is back to being x again. X is about 0.69. Divide both sides by x. 2x equals x. Divide both sides by x. It's not divided by 0. And I get 2 equals 1. And life is good. Whoa. Whoa. This infinite stuff. What's going on now? Someone says it looks good. I've given someone 2 does equal 1. Oh, fabulous, fabulous, fabulous. Someone says, hang on. Can you just rearrange terms? I mean, in ordinary algebra class, you can. For example, if I did the example I did before, 2 plus 3 plus 4, there's a finite sum. I could think of this as 4 plus 3 plus 2 if I wanted to, just rearrange the order, that's fine. Or I could think of this 3 plus 4 plus 2, or I could think of this 2 plus 4 plus 3. I can rearrange as much as I like. But here's the thing. So far, correct, except am I allowed to just rearrange terms when I feel like it for infinite sums? Does this belief about algebra for finite sums work for infinite sums? And again, I guess the question is no. Things get mighty tricky. As soon as you start trying to apply the ordinary rules of algebra and arithmetic to infinite sums, things can get strange and wrong. And as people are saying in the chat, there's something different about this big infinite sum here, that they have to say it's conditionally divergent or only conditionally convergent, sorry, the words there. Maybe that means something strange, but the people have to think long and hard. When do the ordinary rules of arithmetic apply to infinite examples? Things can get strange. But that's the fun of calculus. I love calculus in the sense that if you want to play the mind games of the infinite, does your intuition still hold or doesn't it hold? When will your intuition work, when will it not work? Because often, as people found in the 1800s, things can go wacky. All right. I'm not going to worry about it now. Let's just move away. Let's do proof by experiment. Proof number 8. We have 16 minutes to go. Looks like all my proofs have fallen apart, but this one's going to do it. This one is going to do it. Here goes. Here's a proof by experiment of 1 equals 2. All right. Here are 2 wheels. What I'm going to do, they've got wheels with arrows. Right now, the arrows are pointing upwards. I'm going to rotate this wheel around the circumference of the other one, just roll it around, all the way around. Hopefully my hand's not getting too much in the way. Roll all the way around. Oops, I'm doing a good job. There it is. Bingo. And now those 2 arrows are back to being aligned and pointing upwards. So I can go halfway around the circumference. Hopefully get my hand's not in the way. And those 2 arrows are back being aligned, halfway around. Or another way to get that result is the following. Let me roll both wheels together. Just roll them around each other. And this time I have to go the full circumference, the full way around. Whoops, sorry. To have those arrows be aligned back at the beginning. So going halfway around a circumference has the same effect as going a full way around the circumference. Oh, beautiful. So half circumference equals a full circumference. A half equals 1. Half the circumference the same effect as a full circumference. Double everything, 1 equals 2. Done. Proof by experiment. Love it, love it, love it. Finally there. Are we? This one is weird. This one is weird, I will admit. Something about orientation, something about compound motions. Here's what's really going on. I'll help out with this one. This one takes a while to think through. It is true that I can just move halfway around the circumference to get those arrows aligned. But let me do something sneaky. As I roll this wheel around that one, let me rotate this wheel. This wheel is going to turn this way as I roll that one around. And what the effect is this. It looks like I'm doing that. That if I just do half a circumference and then undo that rotation I did on that wheel, bring it all back, then I'm back to this. So what I was really doing was combining motions. This is actually a combined motion of this motion over halfway round and this wheel being turned halfway around. So actually, this is a mystery of compound motions. It really was actually, it takes half the circumference for the arrows to be aligned. Yep. It takes half the circumference for the arrows to be aligned. It's just that I happened to turn this picture upside down as I was going along last time. So I was being sneaky. It really is only a half equals a half, which I guess I proved 1 equals 1, which I think is true, but not what my goal was for tonight. All right, okay. In which case, we'll do another proof by experiment. Here's an anti-proof. This time, I'm going to start by proving that 2 doesn't equal 1. And for that, I need to stop sharing my screen so you can see me. All right, hope you can see me. Here's a very famous trick. It's called the waiter's trick. Here is a randomly chosen mug from my shelf. So just don't bother reading what's on the mug. Okay. All right, so what I'm going to do is I'm going to stick my feet firmly planted on the ground and get my earphones out of the way. And I'm going to give this mug 1 full rotation with my arm. And I believe that's 1 full rotation. There it is. Now look at me. I'm kind of contorted and all twisted. Do you think I could give this mug a 2nd full rotation in the same direction without taking my feet from the ground? What do you think? Ow, 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 yay, no. Oh, whoa. Yes, the other's doing it too. Someone's actually doing it as well. Yes, I had to go over my head. I can actually do 2 full rotations and end up back in this untangled state. 2 full rotations is actually equivalent to me having done no rotations at all. 2 full rotations is actually topologically equivalent to 0 rotations. And in fact, if you want a really cool dance move, so here's my can of kombucha and here's my coffee mug, do it at the same time. Woo! And you can do a really cool move on the dance floor. You know, this is just a lecture in math and dance. Yes, kind of cool. Actually, there's a traditional dance in Southeast Asia called the candle dance, where dancers actually have balanced candles in their hands and actually do that exact motion with rotating those candles around. All right. So that means I've just proven that 2 rotations is actually equivalent to 0 rotations. 2 equals 0. So let me share my screen again because I need to write down 2 equals 0. We've just shown that. All right. We've just established that 2 equals 0. So 2 doesn't equal 1, except let me divide both sides by 2. 1 equals 0. Let me add 1 to both sides. Oh, 2 does equal 1 after all. Done. Beautiful. What do you think of that one? Modulus. I'm being a bit silly. It is true that 2 is, as rotations, is equivalent. I shouldn't say equals by the same way. It's equivalent to having no rotations. And turns out, if you study mathematics like the topology of rotations, that yep, 2 rotations is equivalent to 0 rotations. That's well known. They're equivalent objects. However, me trying to turn that into a statement about arithmetic being equal is a little bit naughty of me. Okay. All right, okay. Experiments failing, 2 experiments fail. Don't worry, I've got 3 more proofs and I will convince you 2 equals 1. Here's a proof by area. Proof by area. So what I've done here is I've just drawn a great big rectangle. I've chopped that rectangle in half with a diagonal line. In fact, I even chopped the rectangle into 4 smaller rectangles, and the diagonal line chops this purple rectangle in half, and it chops this purple rectangle in half. So what do I conclude here? Well, I know diagonals will chop the big rectangle into halves, so all this top stuff is the same area as all the bottom stuff. And each individual purple rectangle is chopped in half. That top stuff there equals that top stuff there. The top stuff there equals that top stuff there, which means, that means what's left over the top, that yellow there, must be the same area as that yellow there. Because everything's being chopped in half, only leaving me the yellow areas, which case they better be the same. And how big is the yellow areas? 2 by 1, 2, 3, 4, 5, 6, 7, 8. 2 by 8 must be the same area as 3 by 5, 3 by 5. So 16 equals 15. Let's subtract 14 from both sides. 2 equals 1. Done. There's a nice, simple, clean proof. Like that one. That's a good one. What do you think of that one? The gradient of the lines is not the same. For all those in the typical regions, they call it gradient. For all those in the US, they call it slope. The slope of the line, the gradient of the lines are not the same. Yeah, I'm being naughty. I'm being very, very naughty. I drew a picture with very big, thick lines everywhere. It turns out this line here isn't actually going through those corners precisely. In fact, you can kind of see there's a little bit of wonkiness right in there. It actually misses that intersection point. But it misses it by just enough so that the areas of these things won't be 16 and 15, probably more like, I don't know what, like 14 and a half and 14 and a half or something, whatever it is. I'm just cheating. Because I did big, thick lines, it looks like to your first impressions, everything's working just fine, but I was being sneaky. If you try to draw this picture precisely with very thin pens and all the rest, you'll find everything I'm claiming is not working there. All right, that diagonal line was just being naughty. All right, don't worry, I'm still ready. I've got 2 more proofs, and I'm going to convince you in the remaining 7 minutes that 1 does equal 2. But let's do a very abstract argument now. Let's make our brains hurt. Here's a proof by pure thought, and I'm going to ask a strange question. What is the largest counting number? And here's my strange answer to that question. 1 is the largest counting number. So I'm going to prove to you that the answer to this question here is 1. The number 1 is the largest counting number. Here's how my proof is going to go. Now, it's going to be abstract. So there's my claim. I claim that 1 is the largest counting number. And here's the method of my proof. I'm going to show that no other number can be the largest counting number. That 2 can't be the largest counting number, that 7 can't be the largest counting number, that 17 can't be the largest counting number. That will only leave the number 1 as the only possible answer to this question. So let's suppose n is a number not 1, a counting number that's not 1. That is, n is a number bigger than 1. Could be 2, could be 19, could be 446, whatever it is. All right. Well, if we've got a little inequality here, let me just multiply both sides by n, because that shows then that n squared is bigger than n. N times n is bigger than n times 1. Oh, n squared is another counting number bigger than n. Oops, we just thought that the n can't be the largest counting number because I just found a bigger one. All right, any number that's not 1 can't be the largest counting number. This leaves 1 as the only option for the largest counting number. The largest counting number. Okay, so you're getting a class in math and dance and hieroglyphics today. Look at my handwriting. So 1 is the only option for the answer for the largest counting number. So 1 is the largest counting number. 1 is then bigger than 2. By my proof, everyone knows that 1 is smaller than 2. So I guess the only way out of this predicament is that 1 and 2 are the same thing. Beautiful, beautiful, beautiful. I am done. Surely proof number 11 is doing this. I think n being bigger than 1 certainly captures n is not 1. If it's a counting number, the counting numbers are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I think that captures n not being 1. I think I'm okay there. What about n minus 1? Yeah, I don't know what to say about n minus 1. What about n minus 1? Oh, Michael's got an even deeper issue. Yeah, the trouble is with my question. I think Michael's thinking, who says my question should even have an answer? We presumed there was an answer to the question. What is the largest counting number? And I went with that assumption. I assumed we had a largest counting number and showed it can't be 1. Therefore, that leaves 1 as the option. Thing is, you know what? Not every question needs to have an answer. I think that was a faulty assumption. Maybe the fact is there is no largest counting number. Okay. All right, I promise to leave room to actually show the math salute if you'd like me to. That was proof number 11. I feel like you've shot me down on everything so far. But right now, in the final 2 minutes, I've got a couple of minutes space left for questions. Here is proof number 12. This is the proof that is going to convince you that actually I'm right, that 1 equals 2. I really mean it. This one is the one that's going to settle all doubt. You may be saying, who is this foolish fellow with an Australian accent rambling on that 1 = 2 11 times over? Every time he says something, it's wrong. This one is not wrong. This is my actual proof. Are you ready for it? I need a drum roll. Can someone just type in the yes? If you're ready for it, I will show you my proof number 12 that 1 = 2. All right, somebody will do it with their hands. It's a proof by shopping. Here's my shopping proof that 1 = 2. This is a true story. In fact, I'm so in awe of this true story, I'm going to just put the story up on the page and be silent so you can just read it for yourselves. Here's my proof by shopping proof that 1 = 2. I can't argue with that. I cannot argue with that one. Yep, 2 is the same as 1. There it is. That's real life for you. Yes, 1 is the same as 2. So what can I say? What can I say? You shot me down on 11 proofs, actually 12. I gave that bonus algebra one. But there we are. Proof by shopping says it all in the end. So I'm going to say thank you very much for coming with me on this misguided review of mathematics, from kindergarten math to advanced calculus to abstract pure thought. You are such troopers. Thank you so much. There are many people in the world, and whoa, oh, golly, that's a bold claim. Yes, well, okay, but if you do believe 1 = 2, this is great for students. If 1 = 2, then add 1 to both sides, you get that 2 = 3. Then add 1 again, you get 3 = 4. And add 1 again, 4 = 5. You get that all numbers are equal, which means on any exam, if the answer is a numerical exam, you can write down any number you like and you'll be correct. So you're about to get 100% on all exams if you can convince your teachers. Good luck. Good luck on that one. So on that note, thanks everyone. I'm going to stop there. Feel free to ask me questions. Feel free, I'll hang on for a couple more minutes if you like. Thanks for being such wonderful troopers. Really appreciate it. Lots of fun. And thank you, Mathagon, for hosting this. What a platform. Whoa.
Thank you, James. That was such a delightful hour. It goes by so fast anytime I'm doing math with James. And I put in the chat at one point that, you know, each one of those proofs could be a whole lesson and a whole exploration for students, obviously, depending on the age of the student. So thank you for doing that. We have a couple hands raised, so I'd love to call on those hands. Before people go, I just want to give a quick plug, and then I'll call on the hands. This is the first in a whole series of guest speakers that Mathagon is sponsoring over the course of the school year. And I'm so excited about the mathematicians that we have who are coming to join us. October 20th is Simon Singh, Sunil Singh, October 27th, no relation, but amazing math educators. We have Mary Kemper in December, Maria del Rosario Zavala in January, Dan Finkel in February, Katronia Ag in March, Desiree Harrison in April, and Jennifer Suh in May. So really an amazing lineup of folks in the math education space that we are so excited to hear what they have to offer. What I love about this talk as the first one in the series that Mathagon is sponsoring is it's about play and joy and discovery of mathematics and just having fun and seeing what happens. And that's a lot of what we're doing at Mathagon, just encouraging the play, as you can see on the screen here. It's the mathematical playground. So go explore Mathagon. If you go to for teachers and events and webinars, you can go learn a lot more about using the Mathagon tools. So thanks for coming. I'm going to call on folks who have their hands raised. If James is open for doing a couple minutes of questions, that would be great. So let's start with Finn. Yeah, Finn, feel free to unmute. And
is there a wrong solution for the last proof that 2 = 1?
For the shopping one, or the one before that? Well, that's the question. What if there's a 3 for the price of 2 sale? What would happen then? I like your question. I'm not sure what a wrong solution means, but there certainly might be different ways to think about it. And if they did crazier sales, what was a 17 for the price of 8 sale? What would what would we do then? That would be great. That's a good question, Finn. All right, think about it. Let me know. I'm easy to find on email. Feel free to email me anytime. with your thoughts. I'd love to know how your brain thinks on that stuff. That'd be great. Thank you.
Thank you.
Thanks, Finn, for participating. Great to hear from you. And Zita Zara has a hand raised. Love to hear from you again.
I just wanted to say, like, with the one with the circle and the rotation, because I do magic at magic school, it's based on like a similar illusion. When people, yes, with that one, sir, it's like, when they have two people sit together and then they imagine that you touch one person and the other one feels they're being touched at the same time. But the magician has touched the person before and then asks the question, if you've been touched, raise your hand, but at different points. And then the audience thinks there's some kind of telekinetic like connection, but it's actually just messing with time. I don't know. I just found that very interesting. I just wanted to say that.
I love it. Absolutely, yes. And this maths loop, by the way, I should point out, I did not make up. This is something that's in schoolyards and so forth. It's a schoolyard trick. But I also point out that I have to notice that the famous mathematician, what's his name? David Copperfield has started doing this in his magic trick as well. And I've also seen it. There's a book series in the US called something for Dummies. And there's a book called Magic for Dummies. And they actually have, I think, this maths loop in there now. So it's been making the rounds. I mean, it's been around for decades, obviously. But I did see that someone in the chat wants me to explain the maths loop. Is that my next question, perhaps? You should make it my next question. I'll do it. Okay, I'm going to give it away. We're friends. I'm going to give it away. So when you put your arms out front, no tricks there. When you put your right hand over your left hand, no tricks there. But obviously, the tricks are happening in the next part. What most people do when they go palm to palm, they twirl their thumbs in opposite directions. That's very natural in us humans to do. I'm not. I'm actually twirling my thumbs in parallel to my left. Now, on your screen, it's going to look like the opposite direction, but there's in parallel to my left. So if you take your top hand, just put your thumb down the normal way. All the tricks are with the bottom hand, the left hand. The thumb goes towards the palm, towards your left, slides down your palm, and then comes down. It takes a little while. You have to practice like 20 times before you'll get there. You do it one hand at a time. You'll get there, and then you'll do it smooth enough as I can. And then once you have that knowledge, it's beholden upon you to then start sharing the International Maths Loop with everyone in your community tomorrow and spread the word. Spread the word of the International Maths Loop. Cool.
Awesome. Thank you, James. I probably should give, I gave a Mathagon plug at the end. Let me just do another share of Global Math Week, which is coming up. So if you enjoyed this chat, what is great about a Zoom is people can quietly leave and you never know. And so the feedback that I get in a webinar, when the numbers stay the same, or if they drop off, it's good feedback. We had steady numbers the whole time, James. People were engaged and interested and having a great time. So if you're still here, which is a lot of you on the screen, you will definitely enjoy all of the things about Global Math Week 2021. I'll drop that link in the chat again, but it's bound to be a spectacular week of math joy around the world. So go check that out as well.
Absolutely, please do. Thank you, everyone. And yes, there's lots of good proofs out there that 1 + 1 doesn't equal 2, and there's also the other ways of proving that 1 does equal 2 using isosceles triangles and things. So if you've got a favorite proof you want to share with me, like I said, I'm easy to find on the internet. Feel free to email me. And it's great to have a conversation about this stuff. It's just this quirky stuff is so fun.
I just want to say a huge thank you. It was so amazing because I love math so much and I've never met somebody so passionate and creative. I don't know. I just wanted to say I'm so inspired. It's 2 o'clock in the morning by me, but I'm awake and I feel running out saying I love math.
I've ruined your night for you. You're so welcome. And thank you for being such a fabulous young budding mathematician. I'm honored to have you here tonight. Thank you. Keep up your fabulous thinking and your fabulous work. You're an awesome math mind.
It's a credit to the inviting nature of James's presentation and the joy of math. And we have students at all ages who are comfortable participating in this. So a credit to the math joy that is being spread around the world. So thank you again, everyone. Hope to see some of these names and faces at our future guest speaker events down the road. It's been a pleasure doing some math with you all, and hope we can connect down the road. Thanks again, everybody.
You bet. Good night and thank you, everyone.